Most blockbuster sci-fi relies on a healthy dose of space magic. Ships jump to hyperspace, sound travels in a vacuum, and gravity always seems to point toward the floor. Interstellar is a rare exception. It anchors its narrative in the strict, unforgiving laws of astrophysics. To achieve this, the director brought in theoretical physicist Kip Thorne. Thorne's role was to replace standard screenwriting tropes with actual mathematics, ensuring these cosmic environments behave exactly as Einstein's theories predict. This commitment to accuracy went deep enough that the physics depicted in the film sparked actual academic research. This published peer-reviewed paper, titled The Warped Science of Interstellar, explains how the movie simulations actually contributed to the study of general relativity. To understand how the movie functions, we have to analyze its science across a spectrum. We can break the film down into three distinct categories: hard fact, extreme plausibility, and pure speculation. Exploring this gradient reveals where the established laws of physics end and Hollywood's survival instincts begin. We start at the hard fact end of the spectrum with Gargantua, the supermassive black hole. In astrophysical terms, Gargantua is an extremal black hole, possessing a mass millions of times greater than our Sun and an incredibly fast spin. That immense mass creates gravitational lensing. The gravity is so intense that it physically warps the fabric of space-time around it, acting like a giant distorted magnifying glass. This diagram shows a black hole surrounded by an accretion disk. Due to warped space-time, light doesn't travel straight. Ray A pulls over the top, while Ray B bends underneath, creating the glowing halo wrapping the void. The visual effects team fed Thorne's actual relativity equations into their rendering software to compute the exact path of these light rays. This mind-bending cinematic image of a glowing sphere with a dark center is a matter of proven hard scientific fact. Moving further down the spectrum, we hit extreme plausibility. On Miller's planet, the crew faces extreme time dilation. 1 hour on the surface equals 7 years back on Earth, a factor of roughly 60,000. To hit that ratio, the planet must orbit terrifyingly close to the event horizon. Figure 3.2 shows a non-spinning black hole. If Miller's planet were this close to a stationary Gargantua, it would immediately plunge into the void. However, Gargantua spins at 99.999% light speed, introducing frame dragging. The black hole physically drags space itself into a whirling tornado. This drag stabilizes the planet's orbit, allowing it to survive so close to the horizon without being consumed. While this extreme time dilation obeys the laws of physics, it requires an environment balancing on the absolute razor's edge of destruction. This balancing act introduces a mystery on the surface of Miller's planet. How can a world experience periodic 4,000-foot waves when it lacks the extreme winds required to generate them? Gargantua's extreme tidal gravity generates these massive water walls, replacing typical wind-driven weather with cosmic-scale mechanics. Figure 3.4 outlines the effect. On the left, gravity stretches the entire planet, deforming its crust and oceans into an oval. On the right, the planet rocks back and forth, causing the oceans to slosh as massive tsunamis. On this world, the primary killer is the highly localized, violent manipulation of gravity. Finally, we reach the far end of the spectrum, pure speculation. This is where the film requires characters to navigate a traversable wormhole. While mathematical models like the Einstein-Rosen bridge allow for wormholes, the gravitational field inside one would normally be strong enough to instantly crush any matter trying to pass through. To get the crew through, the film introduces a speculative workaround. It implies that an advanced civilization uses exotic matter, or negative energy, to generate outward pressure, holding the throat of the wormhole open. When Cooper descends into the black hole, the plot demands his survival. Figure 3.12 maps out the speculative interior. While relativity predicts a lethal BKL singularity, the film posits that Cooper avoids this fatal zone to interact with a speculative 5-dimensional reality. At this deep level of the universe, our actual knowledge runs out. To keep their characters alive, the filmmakers had to invent new theoretical loopholes where the math went dark. We've traveled the full gradient, from the hard facts of gravitational lensing to the pure speculation of 5-dimensional space. The filmmakers stretched the rules of physics to save the heroes, but the forces trying to destroy them, the crushing weight of gravity and the relentless, isolating march of time, remained entirely real. The true achievement of Interstellar is its ability to visualize Einstein's mathematics for a mass audience. By treating the math with respect, the film proves that the proven laws of our universe are far stranger, more hostile, and more awe-inspiring than anything a screenwriter could invent from scratch.